So let's say we have two like circularly plated capacitors and we're charging them, right? So there's going to be current, entering through the wires, right, onto the plate, which would cause it to charge. You remember usually for like a simple RC circuit, the current would eventually like die down, right? Like you would plug it in and the current would eventually level down to zero as it gets fully charged. For this scenario, we're just going to assume the current is constant, which is possible, right? If you somehow like increased the voltage of your battery over time, the voltage would get bigger and bigger, so the charge that the capacitor holds would get bigger and you can get constant current. And if we want to find the magnetic field, right, at a point near the wire, right, and I know it doesn't look near the wire, but we're going to assume it's very close enough to the wire so that we can use Ampere's law, right? And with Ampere's law, you make your you make your loop, and you want to use symmetry. So I'm going to make it a circular loop because I know the magnetic field is going to be the same around that loop, and I can just do Ampere's law, right? So, the line integral B dl is going to equal mu naught times the current enclosed, and because the b is constant, because of symmetry, I can pull the b out of the integral, and I get 2 pi r over mu naught I, and I get my classic result, right? The memorized mu naught I over 2 pi r. Now, hey, let's say I want to find the magnetic field right in between the capacitors, right? Like where there's no, there's no current really flowing through it. Well, if I use Ampere's law, if I make my loop, right, like how I normally do, right, what I find is that, well, hey, there's no I enclosed. So if there's no current being enclosed, that must mean there's no magnetic field at that point. And, we know that's not true. We know that's not true just from the simple fact of, well, hey, if there's current here, right, this, section of current is a certain distance away from the that point. I'll just call them X and Y, from point Y. And if I use Biot-Savart law, right, Biot-Savart law can help us find the magnetic field due to like current and charge. If you use your Biot-Savart law, you could find, theoretically, if you go through that integral, you could find the magnetic field, right? The point is current creates magnetic field. So how can there be no magnetic field at this point if there is current right here, and we're going to assume there would be current coming out the other way, right? How can that be the case, that there's zero magnetic field? There is magnetic field there for sure, and what we found is that for a circularly plated capacitor, it has to be circularly plated, the magnetic field at point Y actually equals the magnetic field at point X. Which is pretty crazy. That's a pretty crazy result. And Maxwell, this I forget his name. I think it's James Maxwell. I don't really remember. What he actually found is that, well, hey, current is not the only thing that creates magnetic field. Just like how changing magnetic flux through a certain area induces essentially an electric field, right? Because it induces an EMF, and an EMF is just that integral, that line integral of the electric field across your loop. So just in the same way that a changing magnetic flux can create an electric field, Maxwell hypothesized and confirmed that a changing electric field can actually induce a magnetic field. And this actually explains why there is a magnetic field here, is not just like, I guess to my point right earlier about how these wires are creating a magnetic field here. Well, how is it how is it exactly the same as a magnetic field here, despite there being no current flowing here, right? How can it be the same if it's not the same point and there's empty space here? It's because of the changing electric field through these capacitors, right? As charge will build over time, which will change the electric field. So really quickly, let me show you Ampere's law, just kind of modified. Ampere's law, the Maxwell addition. I'm not gonna derive it. I don't know where it comes from, but like mathematically, like I don't really know how he got to this equation, but he found that, well, you have your I enclosed alongside epsilon naught times d phi dt, where d phi is really the change in electric flux over time. So if we were to use Ampere-Maxwell's law, right? If we were to use Maxwell's addition in this scenario, well, hey, you could still use your symmetry, right? I know there's going to be circular symmetry, so I could say, well, I can pull out the B over 2 pi r. Sorry, times 2 pi r. I'm going to do the over 2 pi r in a second. So just to be clear, r is like the distance from the center to point y. And then mu naught, there's no more I enclosed, right? There's 0 amps of enclosed current, but now there's this electric field that's changing, this electric flux specifically. And electric flux, as we know, is E dot A, right? And where A really represents the area of our loop, right? And the electric field is the electric field that's hopefully changing in order to get a magnetic field going. So, okay, how would we, what is the electric field, by the way? The electric field is really, the electric field, according to Gauss's law, would end up being lowercase sigma over epsilon naught times area. And lowercase sigma represents the charge, the surface charge density, right? The charge per unit area on these plates. Well, in that case, well, you know, the electric flux, well, the charge per unit area multiplied by the area of these plates, that just ends up being whatever the total charge is, Q, on those plates. So if I take the derivative with respect to time on both sides, I get my d flux dt. And now I'm taking the derivative of the right-hand side. Epsilon naught's a constant, so the only thing I'm taking the derivative of is charge. Well, what's the derivative of charge with respect to time? It's current, right? It's current over epsilon naught. And hopefully that makes sense, right? It's because, well, over time, there's going to be more and more charge accumulating, and if this current is constant, well, it's just going to end up being like the current multiplied by the time, right? Because it's a constant current, and current is the movement of charge, right? So more and more charge is moving onto the plate at that rate. So I can now substitute this back in, epsilon naught times the current over epsilon naught, and the epsilon naughts cross, and I have mu naught times I, right? So B over mu naught times I over 2 pi r. So same result, and this is thanks to the changing electric field. Now, this term right here is known as a displacement current, which is kind of a strange name, right? Displacement current. I don't even know what that means. Obviously, it's not really a real thing. The main idea is not that current, like we know current creates magnetic field, but it's also the idea that magnetic or changing electric fields can create magnetic fields. So, did I say that right? Changing electric fields can create magnetic fields. Yeah, I did say it right. I always mix them up. So yeah, that was just a quick, introduction and demo of Ampere-Maxwell Law. So yeah, thank you for watching.